All right, guys, so it's 2 o'clock. Let's get started. So you guys are the first section, Mondays and Wednesdays. This is week 3, and we are doing a lab today related to KNN. You will have a homework assignment. This will be homework number 2. Should be pretty easy, like very easy homework. But I will assign it today, so I'll give you a little bit of time to work on it today as well. So let's kind of see where we are. Okay. Um, so you guys have been going through these problems, practicing. We've started coding now, right? And you will see that today even more. Weka was one of the topics, and you have an assignment that's due today. It'll stay open until Sunday. Okay, so you can submit until then, but try to submit as soon as you can. And then we covered the machine learning pipeline on Monday. Yeah. And then we are currently on this module, KNN. So this is your first algorithm. It's the K nearest neighbor algorithm. We went over the Euclidean distance on Monday, right? We covered like the theory of it. We looked at the formula of how it works. And today we will be using it on the iris data set. So we'll be implementing this. Next week, we'll look at unsupervised learning. So still working through the idea of vector space models, but this will be a different kind of approach when we don't have labels. Should be a very interesting example, actually, also related to cybersecurity. Following that idea of building an intrusion detection system. So this one will be looking at the payload, essentially, of what might be in there, for instance. And so, yeah, so we'll cover that one. Should be an interesting discussion next week. We may also start looking at performance metrics and so on. But today I want to wrap up KNN. That's my goal. So you should understand this algorithm today. Yeah, and so that's the plan. So essentially, I've gone over the slides and everything. I gave you this reading link. And today we're just going to focus on the code. So as you can see here, it's this one, KNN. So on Monday we covered just a basic, main machine learning sequence of steps. We also covered the Euclidean distance. And today we're going to cover KNN and metrics and just kind of implement the algorithm and get a feel for it. All right, if you remember, you had the iris data set for this example, right, which is here. So I showed you how to, you get this file, and then you put it on your Google Drive, and then you mount the drive on Colab. You can see that in that first video on Monday. And then you have the data set available. Okay. So I'm going to start there. So we're going to use Colab today. And this will be your first Colab homework as well. All right, so the homework should be pretty easy. I'm just going to give you another data set, and you have to train it using KNN and this code. So kind of pay attention to what I'm doing, and then I'll provide the link and the data set so that you guys can do homework number 2. All right, so I'm going to click on New Notebook here. All right, I'm going to add a few cells as usual. The runtime, remember here, we just need to use regular CPU. We're not doing anything that requires GPUs, so that's fine. I'm going to click on this button, click on this button here. What's this? All right, and I'm going to mount the Google Drive. So connect to Google Drive via my Gmail. Let's give it a second. All right, here it is. So I'm going to click on this, click on my drive, and I'm just going to copy the path to the file that I want to use. So in this case, I'm going to once again use the iris CSV file. Pretty easy, just to get a feel for KNN. So copy path, and that's it. All right, close this. I'm just going to put the link somewhere here, and that's the path, right? So this is where the file would be located. All right. I'm also going to maybe do some examples with Iris, like getting that data from a module, from a library, just so that you can see that you can do both things. But one of the goals today is to read this file, load it, and then be able to train and evaluate the K nearest neighbor algorithm. All right, so now we can take a look at, so obviously the code is provided, so you just try to understand how it works. That's really the key, and you can always just get it from the repo. So this, click on KNN. So I have several versions. I usually have like multiple versions. We can take a look at this one, for instance, and you can see it's got the basic logic, right? So this was the Euclidean distance function. We need to use that, and then we need to go over the algorithm itself. Okay, so that's essentially the idea. So what I'm going to do here is I'm going to copy these libraries. Okay, and so you can see I have numpy. K means the number of samples that you look at, the number of points, the closest points, and you're going to look at their individual labels to figure out the majority label to assign to your test sample. All right, let's take a look at version 2 of this algorithm here. Yeah, so this one, pretty similar. Take a look at sample 3. This one uses the okay, this is just a Euclidean distance function. And yeah, so let's go with this one because I'm going to be reading the file. So this is actually the complete code that you should reference, so KNN and metrics. Okay, notice there's going to be more libraries here. There's going to be a few little things that we need to do, but this is a good example. So let's go with this one. So libraries that we need, of course, we've talked about this before. sklearn. sklearn is really powerful. It's got a whole bunch of different algorithms, just like Weka did, right, that we can use through its library. Right now, we're just using it more for like pre-processing. If you remember that machine learning pipeline, before you get to the machine learning part, you have to do all these steps, right? And so here I'm going to show you examples of how to get the data using the data sets, but also the goal ultimately is to read it from a CSV. I think we talked about this one already, train, test, split. This is so that we can split the data into 80% training, 20% testing. Notice that I'm now bringing in metrics from sklearn. Iris is a supervised learning type of a data set, and we're trying to predict classes. So we're using these metrics, for classification, the confusion matrix, precision, recall, accuracy, F1 measure. Notice also you may have seen this library in 265, right? In ITS 265, Pandas. It's a really great library for manipulating data, not so much for like training machine learning models, but just for processing data. You guys have taken SQL classes, for instance, right? And it's actually Pandas brings a lot of those ideas from SQL so that you can actually like do queries and joins and things like that of data, so it's really powerful. All right, so this is a great library to learn. You could spend a whole semester just on that. All right, we'll use it here mostly just to bring in the data, do a little bit of processing here and there. The counter from collections, we had talked about this already. This is just so that we can count the number of classes. And notice that from sklearn, we're going to use this function called label encoder. And this function is because we're going to have classes that are Setosa, Virginica, versicolor, and so we want to change those to numbers, right? So the label encoder is a great function for doing that. Okay, so yeah, so let's bring in these libraries. Let's run. Okay, so we got a green check, perfect. Now we can, go ahead and define a couple of things here. Whoops. So I'm going to define the number of the k nearest neighbors, which is 5, and then the Euclidean distance, right? So this is, remember, you take 2 points, and in a vector-wise approach, we calculate the difference between the cells of each of the 2 vectors. So if I have a vector of 4 for V1 and a vector of 4 for V2, right, then V1 minus V2 still produces a vector of size 4. But now this vector has the differences between the individual elements in V1 and V2. Then we square it, and that's still a vector of size 4 with the values squared. Then we sum those values, and then we take the square root. So this is just what we discussed about the Euclidean distance function. Notice that it doesn't use the for loop approach anymore, but it uses a vector-wise approach for processing. All right, so that's great. Okay, so the next step would be the algorithm. So this is the KNN algorithm. I'm going to leave that for later. And the first thing I want to do is just load the data, right? So I want to load the data and start looking at the data, as you can see here. And then once we have the data, then we can start bringing in the algorithm and starting training. So let's go ahead and do that. So I'm going to skip this for now. I'll come back to it. Remember, we're using iris, Fisher's iris. So that's a data set of 150 flowers, the iris flower. Each flower has 4 features: petal length, petal width, sepal length, sepal width, right? And then we have 3 classes in the last column. So there's a couple of ways that we can bring in the data into our code. One way should be to just use the data sets module from the imported libraries. So you can see that there. This we had done on Monday, I believe. You can see essentially I bring in iris, iris.data, iris target, and then when I print X, you can see there should be 150 rows and 4 columns. For the features, we can print a shape. And there you go. And this is really great. Like if whenever you're just trying out an algorithm, you can bring in the data set like this. But obviously, as you guys start to do, homework assignments, projects, maybe, you do some consulting or at your workplace, obviously the data sets are not going to be in libraries, but instead they'll come from someone, right? It's going to be some kind of a file, a CSV, a folder. So we also have to learn how to do that. All right, but this is just an example to illustrate that we have data sets available in libraries. So I'm going to comment this out now. Okay, so let's move on to the next step. There are several different functions that you can use to bring in files into your data set. My preferred approach is always to use pandas. That, I believe, is like the best way to do things. You bring in the data into pandas. Because it's in the pandas data frame, then there's quite a bit that you can do with it. Call it, exploration, data science, etc. Okay? But there are other approaches. As I said, sklearn has approaches. If you notice here, I'm using numpy here, NP, right? So this should be another way of bringing in the data. I need to specify the direct path, of course. Okay, so yeah, open a file, give it to, a file handler in the normal Python approach, read it, and give it to a function called np.loadtxt. The delimiter should be a comma. Skip rows, the first one, essentially, and then print the matrix. Let's try that. And oh yeah. So notice it didn't like the fact that in the last column, column 5, the labels are called setosa, virginica, versicolor, right? It's numpy. Numpy is about like numbers, right? A numerical Python. And so it's giving us an issue there, all right? So if it was all numbers, then it would be able to process. All right, so, but that's where, again, just to illustrate, pandas would be really good for something like this. So I'm going to go ahead and switch over to pandas. Okay, so that's done. So now I'm going to take this approach over here, and I'm going to, actually these two. I'll copy. So here we are. So by definition, pandas has, all these libraries have their own like terminology. In pandas, things are called data frames, like where we would call something a matrix in maybe a numpy or a numpy array. Once you load something in pandas, it usually is called a data frame. That's why this says DF. It implies a data frame. All right, I'm importing pandas. If for some reason, remember, if you can't load pandas, it says that you need to install the library. You'd have to do exclamation pip install pandas. Okay. So now we read in, again, I need to grab the path, paste that in there. Oops. Okay. So pd.readcsv, that's the path, header none, so that would imply that there's a header, but we want to ignore it, right? Header would be like, it says F1, F2, F3, F4, or something like that. And then we print the data frame. So let's go ahead. And as you can see, it actually did do it. And so there's the data, right? So you can see we have from 0 to 150, we have the 4 columns for the features and the last column for the labels, okay? So we have that for the labels. Okay, great. So now I have my data loaded. So that's, excellent, right? So this is something that is always a concern. But once you have a CSV, you create your data set maybe, and now you can load it to your code. Whether you're using PyTorch, whether you're using like a very complicated algorithm, this is how you would load the data. And as I said, this is my preferred way. All right, so now we can visualize some aspects of the data. So let's take a look here. So I'm going to go here. I'm going to Control V. So you can see the data frame, it has some syntax that you have to get used to here, for instance. And there's several ways also of doing this. But essentially, I can look at the data. Notice that I'm doing some kind of a slicing, right? So from one, if I'm looking at the number of rows, from one to the end, skipping the first row, perhaps because we want to skip the titles, right? The names, like supple length, supple width. And then as far as the columns, we slice again from the beginning until 3. So we grab the first 4, essentially, right? And that should be for our X data, okay? So, and then we can change the data type to be float, and essentially, let's run this. Okay, so we got a green check. So now we can proceed to print X, and there it is. Notice that the data set looks, perfect. Looks really great. You always want to confirm that you didn't miss anything, so we can print shape, and there it is, 150, 4. So now we have our X data, okay? The next step is to bring in our Y data. I'm going to go and now take from the pandas data frame the Y, because we always want to have this X comma Y, right? So that's essentially, if you get to that stage, you can now apply many machine learning algorithms to your problem. Okay, so I'm gonna do Y, the same approach. I grab the data frame. Notice I'm slicing again, right, from 1 to the end of the rows, excluding row 0. And then I'm going to grab essentially the fifth column here, because it goes from 0, starts at 0. And so I grab the values, and now that's my Y. So if I print Y, but we do have a problem, right? We have a problem in that the values being stored are still strings. This is not going to work for something like KNN or any algorithm in machine learning, so we have to modify this and convert this to numbers. But that should be easy with our label encoder. Okay, but that's good. So we've made some progress. You always live by the shapes. You know, with Iris, it's a very small data set, so you can actually visualize it, but most data sets are going to be large. If you have a data set that's 4,000 rows by, 40 columns, there's no way that you can really get a sense for it. You can look at segments of it, perhaps, but not anything else. So doing the dimensions, the shape is really helpful. So here we can see we have 150 values as well for the labels. All right, so we've done that. Now we're going to convert the data to numbers by using this thing called the label encoder. Remember, this is coming from sklearn. So sklearn.processing, and we import the label encoder. Okay, so that's the idea. Okay, so let's go ahead. And let's think about how this works. A lot of things in machine learning are object-oriented, so you have to get used to the fact you're going to create an object called LE, which is a label encoder. Do you see that? So that just creates it. And then after that, we are going to give the Y data to LE, and LE is going to transform it from words into numbers. So it changes a label string into integers. There's going to be this notation in sklearn where it has things like fit or predict, but sometimes it uses the two words fit and transform, or fit and predict. And so what that means is that it's doing both things at the same time. So essentially we're saying learn from the data here in Y and then apply what you learned to Y to produce a modified Y. So that's what we do. So hopefully now Y has automatically been changed. And you can see that it learned that there were 3 classes in there. So you want to make sure, right, that you don't have like a fourth letter in there, a dot or something, because it's going to think it's a 4th class. But here it correctly assessed that there were 3 classes, and then it converted them. So now Setosa, Virginica, and Versicolor correspond to the integers 0, 1, and 2. Okay, so that's pretty simple. All right, so I have my X and Y, and they are processed now. Okay, so now the next step is we want to split the data. Remember that we need to train the model, and then we need to evaluate the model. So we can take 80% of the data, which is going to be about 120 samples, right? And we're going to use those samples to train KNN, essentially, or any other model, or use it as training data. How about that? All right? Remember, this is actually a lazy algorithm, so there is no training in that sense. Instead, we're using it, like during inference mode, we're essentially using KNN. Right? So here, there's the train test split. This is going to become a very common function that we will use. So we give it, notice, X and Y. So we give it X and Y. We specify that we want the test size to be whatever. So a common value might be like 2080. So we use 80% for training, 20% for testing. Okay. Random state, remember the idea with random state is that the train test split will randomize the samples every row by default. And if we don't specify a random state, every time it would be different, right? And so by doing 42, we can have some, we always get the same randomization, and that's just, that's a choice. Sometimes you need that, sometimes you don't need that. All right, remember that this function will take x and y and split it into 4 elements, x train and y train, x test and y test. So an x and y for training and an x and y for testing. And this will also be very common in a lot of the things that we will be doing. All right, so that's good. So we're making good progress. So now we have our data, and it's essentially ready for us to view, and then we can start looking at the algorithm. Okay, so here I have y test, y train, x train, x test. So I click on that, and we can visualize the data here. So again, here you can see the data, but in the future we'll probably just print the shapes. So here is the labels for testing. These are the labels for training. This is the X for testing, or for training, sorry, and then the X for testing. So that's our data. Any questions so far on the data? Okay. All right, good. So now, if we take a look at that, we can see that the next step is we're going to need a function to evaluate the performance. So I'll talk about that in a little bit. And then here we should be ready actually to start using KNN. Okay, so let's go ahead, and this will be the function that we need. So let's talk a little bit about it. All right, so the logic here is a little bit different actually from other machine learning approaches. But here, remember, we have X train and X test, right? So what we want is we want to use the data in X train. We want to use the data in X train, right, to assign labels to the data in X test. Do you guys see that? Now, X test already has its own labels, and that's good because that's how we will be able to evaluate the performance. The model, KNN, will predict the label for the 30 test samples, and then those 30 predictions can be compared to the actual labels of the test set, right? And that's how we know how many samples we got correct. Does that make sense, guys? That's key intuition, right? So that's why we have the data. So essentially, if I look over here, we're going to use the train data for the model, and then once we have the model, we give a test sample to the model, and the model predicts a label, and that predicted label is compared to the real label. Right? So that's the idea. Okay, so we're going to iterate through test samples, okay, and send each one of those test samples into the algorithm so that we can compare it to all the training samples. So here we have, for instance, let's start here. I have a for loop. This is one place where you do use a for loop in machine learning. I'm going to take from X test. Remember that X test is what? 30 by 4, right? So there's 30 samples. Each one is a vector of size 4. So we iterate through those 30. So I'm going to grab the first one, then the second one, then the third one, then the fourth one, and so on, right? And what do I do with that sample? I send it to a function called predict, which is the function that is going to have the KNN algorithm. Okay? So I give that sample to predict. Predict is where we're going to define KNN. And then KNN is going to return the label, essentially. So it's going to return the assigned label. That's why I'm calling it pred here. So it means predict, temporary predict. right? It might have some format here. So that's why we have these indices. And then we're just going to have a list of the predicted labels. So there's going to be 30 test samples. That means we're going to have 30 predicted labels. And y-test also has 30 labels, so we'll have two vectors of 30 that we can use to evaluate performance, okay? So list of labels, append is just a list. We're going to add the predicted label. Maybe it's going to predict 0, maybe it's going to predict 1, maybe it's going to predict 2, and that's it. All right, once I have that, then I'll print it at this stage, but later I'm going to use that to evaluate performance, okay? So here you can see this will print out the predicted labels, and this will print out the actual label so we can view it. Because iris is so small, we can actually see it, right? But in other data sets that will be much larger, maybe for your homework assignment, you will not be able to just look at every prediction and compare it to the real value. Instead, you have to rely on the performance metrics. All right, so we've gotten to the point now where we're ready to look at the k nearest neighbor algorithm, our first algorithm that we want to understand how it works. So we're going to define predict. So I'm going to add predict here. All right, so now I'm going to go over here. Okay, this is the algorithm. I'm just going to copy like the first line, and we're going to go as much as we can slowly so that we can see what's happening, okay? So you can see here, I'm going to grab a test sample. It's going to go into predict. So that's going to be this test x here, okay? And what I'm going to do is I'm going to calculate the distances between test x and all the data samples in x train in this case. So there should be 120 samples. So the way that we do that is by creating a list comprehension, okay? So you're going to see here for x and x train. So I'm going to iterate through the 120 samples in the train set. And I'm going to take each of those and compare it to this one test sample that I'm looking at currently of the 30, and I'm going to measure the distance. So I compare 1 to 120. I'm going to end up with 120 distances. And now, so it's like here, right? So you guys, let's say you're 120 people, and then I come in here, and so I'm test X, and all of you are this, X and X train. So now I measure the distance between me and all of you. Once I have all these distances, maybe you and you are the closest to me, and that's it. That's essentially what's going to happen. So let's take a look at this step here. Let's see. I'm going to print test X here. This is just debugging. We'll remove this. So print test underscore X. Okay. And I'm going to put in an input here just to hold the prompt program. All right, so let's add this function. Okay, so that's added. Now I'm going to do this. And you can see, essentially, I'm debugging the program, right? This is the vector that I just grabbed, x test. So it's 6.1, comma 2.8, comma 4.7, comma 1.2. That's the value, test x. And now what I need to do is I need to compare it with all the 120 vectors of 4 and x train to obtain this over here. Okay, so let me stop this one. And now let's modify this a little bit. So now what we want to do is we want to look at distances. And there should be 120 distances in here. Like that. And that's actually, well, I'll put an input here. All right. So let's go ahead and modify that function. Now let's run this. And you can see here there, right? So I've created now all these this vector of distances. So this one is 4.19, 3.68, 0.76. Do you see that? So that's a shorter distance. What does that mean? It means that my sample seems to be closer out of these three to the third vector in there. Do you guys see that? That's essentially how it works. Notice this one is 3.55, so it's further away. This one, I think I saw one that was, well, let's see if you guys see anything. One that's really far away. Some of them are closer. Yeah, so they seem to range between 1 and 3, right? 2.68. Yeah, but essentially that's how it works, right? So now I have all these different distances. That's KNN. That's like half the heart of it, essentially. So now the question would be what we want, going back to the example at the beginning, I have these first three. I really don't care so much about the value 0.76. What I care about is which sample that was, right? And so I know that I just need the index, right? So this is index 0, this is index 1, this is index 2. Because the data, the x and the y are aligned, right? So all I need is the index, 0, 1, 2. If I have this index 2, then I can go to the y vector and grab index 2, and guess what? I have the corresponding label. It may be that this one is a setosa, for instance. So now I know, oh, great. One of the, my sample is closer to setosa vectors. Does that make sense, guys? That is the essence of the vector space model and the essence of KNN. Are there any questions on this one? It's so easy, right? So it's very simple. Are there any questions? Okay, perfect. So seems like you guys are getting it. So now that's good. Now let's go back to the algorithm. We can remove this and let's look at the next step. So you've seen that the values kind of look like this. The next step is essentially to sort the values. But since we don't really care so much about the values, and instead what we want is the index, right? We just need a function that can help us with that. And lucky for us, in numpy and many PyTorch, many libraries, we have functions that do exactly that. They will sort by the values, but then return the index, and that's really great. So here, sort by distance and return the k closest neighbors. Arcsort returns the indices of the k nearest neighbors. So here you can see I'm just creating a variable here to hold those values. I'm going to invoke np.arcsort. I provide this distances vector here, and then this little trick that I'm adding here is slicing once again. So as you can see, slicing is very helpful. Why do I need to do slicing? Well, let's kind of think about it. So I'm going to use, I'm going to put a print here. And I'm going to just do this without the slicing so that, I can just simply copy function like that. And I'm going to put an input to hold the program. All right, so now, before we had the values, now hopefully we will have the indices. So I clicked on that. Now I do this. If you notice, now it gave me not the values, but the indices. So it's telling me 79, 90, 39, 73, and 80 have the smallest distances. You guys see that? If I didn't use the slicing, then it should give me all 120. And you see there's, so this is actually the, the sorted samples. And we know, and then I'm just slicing the first 5. Once I have them, then I can use these indices to go into the labels vector and just extract the labels. Okay, so I'm going to go ahead and do that. I'm going to pause this here. I'm going to add this back. Okay, I'm going to get rid of that. Comment. All right, so now, as you can see, we've selected the top 5. We're almost there, right? So we're literally done with KNN. How simple is that? So now the next step is to kind of just grab the labels. How do we do that? The labels for X train exist in Y train, right? And so we just need to know, we had some indices here, 79, 83, and so on. So we iterate for I in these values, like we grab the individual values in there, right? And we're going to index Y train, and that way we extract the individual labels. Okay? So now I'm going to go ahead and print these labels. Print the labels. I'm going to add an input here. Okay, just like that. So we run it. Run that one. And as you can see, now it returned not the index, but the corresponding labels for those indices in the Y vector. Right? So in Y train, so you can see 1, 1, 1, 1, 1. So basically, this is, now we just take the majority class here. So here, there's only one class, 1. So what was that? What was 1? So we go back to the label encoding. It started with Setosa, versicolor, and virginica, right? Setosa. Yeah. So 1 would be what? Versicolor. Do you guys see that? So essentially, the machine learning algorithm has done its job, and now it can take any sample and classify it. And here it classified our sample as 1, versicolor. Now, of course, here we're human, so we look at this and we know immediately that the majority class is 1. But for the algorithm, sometimes we could have 3 1s and 2 zeros, right? So then it has to have some kind of function to calculate the majority class on its own. So that's the final step. We're just going to use this convenient function, counter. So we're just going to say here, so, we're going to add a comment, select the most common label in labels out of the 5. So we just use this function counter from the libraries above, and we assign labels to it, and then we just say the most common, right? The most common element, and that's going to be our label, most common. Okay, so now this, if we print most common label, that should be 1. So print most common label. Okay. I'm going to put an input just in case. All right, so I run that. So that's the function. And there you go. The most common label is 1. There it is. Because this provides like a tuple and it provides an array, that's why in the code we are going to need these 2 0 indices so that we can grab first with a 1 element in there and then the first of the 2. All right, so that's where these 2 zeros come here. We're indexing essentially. Okay, so 0 just grabs. Notice that there's like a tuple inside a list. So we grab that tuple inside the list with the first 0. And then with the second 0, once we have the tuple, we grab the first element. That's what this code is about. And so, yeah, so that's essentially the algorithm. So what do you guys think? That's one machine learning algorithm, KNN. Now you know it, and that's it. That you can use it. It's powerful, actually. There's a lot of applications where KNN is more than enough. Okay, and this is not a neural network. It's not a fancy Bayesian algorithm or support vector machines. Notice how simple it is to implement. You know, it's not like other algorithms are going to be a little bit harder to implement, right? And so, but this one is super easy and just as powerful for supervised learning. All right, so that's the algorithm. So I'm going to remove this input. So now we're ready actually to run the algorithm on all the data. So notice over here, remember the logic is every test sample out of the 30, right, gets compared to all 120 trained samples. So we take like the first test sample, compare it to 120 trained samples, get a class. Then we get the second test sample. We compare it to 120, the same 120 training samples, get the label. Get the third test sample, compare it, and so on. Okay? So here then I get the class, then I grab the class, and remember I'm just going to add it to a list. Okay? And then I'm also going to have y test, which is the real data. So I have predicted and real. So this should be ready to go now. So that algorithm, yeah. So green check, so the algorithm should be complete. KNN. What's the error? It's commonly. All right, let me try this again. Oh, sorry, yeah, I didn't return it. Okay, yeah, so return most common label. Printing it for some reason. Okay, so yeah, so I need to return the label, right? And then this label is going to be added to the list. So now it's update, the function is updated, and there we are. So as you can see, I'm printing the predicted values and the real values. Try something here. Better. All right, so I was printing like the data type. So I just extracted the value. So I have the values now. So if you notice, we can actually, just for this one example, because there aren't that many test samples, just 30, we can actually manually do the comparison, right? So we can see in the first one, there's a match. Second one, there's a match. Third, there's a match. Fourth, fifth, sixth, seventh, and so on, right? So there seems to be, can you guys see maybe a case where there's a mismatch? It's hard to tell, right? It's hard to tell even if we only have 30 here. So that's why instead of doing this like manually and trying to figure out how many we got correct, we can just use some performance metrics, precision, recall, F measure, right? And so that's what I'm going to do now. I'm going to introduce a little function in Python that we can use for that. So this function, by the way, you can use all semester. It works really well because it's based on numpy, so you can always just change your data back to numpy and from torch once we get there. And so then you can just use this function to print the results. Okay, so notice here I printed this. I may need to change the data types. Oh, actually, we're going to do this. This is going to be useful. Okay. Yeah. All right, so let's add this function. So let's describe it a little bit. The function essentially, you can, as a variable, provide the algorithms, such as KNN, naive Bayes. So that's helpful when you're like, if I give you another assignment later on where I tell you to use 3 algorithms, it's going to be handy to know which which one, the results that you're looking at, it'll be useful to see where they came from or what algorithm they match to. All right, so so the function is going to be print stats percentage train test. That's just some name. And you provide essentially y test and y pred. So what are those? They're essentially these, right? So the 30 that you predicted and the 30 that you already had, the actual label. So you provide both of those to the algorithm, and then the algorithm just calls several functions from sklearn. So it's going to call accuracy score, okay? And accuracy score is going to take y test and y pred, the confusion matrix, which will take y test and y pred, the precision score, and the same, right? So all of these will take both the predicted vector and the real vector. All right, so let's add this function. So it's been added. Now the next thing we might want to do is change this list of pred labels. It's actually a Python list, whereas this one is a numpy array, right? So we can see by the data types that they are different. So let's change the first one to be a numpy array. So that here. Yeah, so let's do it. So you can see I was calling y test is, I usually use the same terminology, so it's going to be y test for the real, y pred for the predicted. Okay, but this one, list of pred labels, I'm going to rename as y pred and also convert it to a numpy array. So now I'm going to convert it and print both of them, and now you can see they're both in the same, have the same data type, and now it's actually easier to see if we had any misclassifications. So here we have all of these seem to be, so essentially we have like perfect accuracy, right? But it seems like, it predicted all the correct labels, but we need to have some metric to evaluate that. So now we're going to pass these two to our function that we just created called printstats percentage train test, and this should print out the results. And these results are going to be pretty much the same results that you had when you were using Weka, right? So that's the great thing. So the same metrics that you had in Weka, you'll have here. All right, so let's go ahead and do that. So that's the last part of the code. Here we are. So we call the function printstats percentage train test. I'm going to say that this is KNN. And notice I give it y test and y pred, these two vectors, and then I just print the results. And there it is. If you notice, it's got the familiar confusion matrix. So, and this corroborates what we saw visually, right? That there were no misclassifications. So that means all values that are on the diagonal, there's no values off diagonal, and we can see that accuracy, precision, recall, F measure are all one. So essentially, it means this perfect classification. Let's run it again. Let's just see if we can get an error, right? So I'm going to show you, let's see. Let's run this one again. On that one. Again, right, the same. Now, let me go back to the point where I load the data. And what I'm going to do is I'm going to change the, where was it? Where I do the train test split, I'm going to change the random state to be something else. I'm going to change it to 24. So this time it's going to randomize it in another way. right? So it should be another, some samples that were in the test set, now maybe they're in the train set. So the goal here is to see if we can get at least one misclassification. Okay, there it is. Ah, there we are. So you can see because I changed the data just a little bit, right? I randomized it in another way. Now I get one misclassification, one value off diagonal, 97, 96, and so on. Does this make sense, guys? And this is why, you know, notice that all I did is change the randomization and now my performance went down. So in a competition, you know, somebody could have been using the other randomization, they get 100%. Someone else uses this randomization, they get 97%. But does it really mean that the first person won? Not really, right? It was very dependent on the randomization, so that's why it's a good recommendation to run it like 10 times. See that? Does this make sense, guys? That's the first algorithm. That's KNN. You now know machine learning. Well, you know one algorithm, right? So, and an easy one, and still a powerful one. All right, so that completes KNN, your first algorithm. Are there any questions? Is there anything you don't understand? Or next week we'll cover K-means and unsupervised learning. So, a slightly different approach. All right, so if there's no questions, that's good. So now I'm just going to assign today's homework, which will be pretty easy. You have to use this same algorithm, but with a different data set. Does that make sense? So that's it. All right, so I strongly recommend that you like type it up, right? In just so that you see how it works. And then of course it's a different data set, so it's going to be different results and so on. All right, so let's do that. So the data set is going to be, and you can work on this. So I'll add it here. So it's going to be this data set. All right, so I'm going to create the assignment link. You'll have 1 week to complete this assignment. Obviously, the hard part, as usual, is dealing with the data, right? So there's a few tricks in here that you have to think about, but it's essentially so you have wine, right? And that's a bottle of wine, I guess, is a sample, and then they measure things like acidity, pH balance, things like that. And then essentially people rank the wine from 0 to 10. So there should be 10 classes, and they're just ranking. So really bad, all the way to really good. But there's 10 classes. And one of the challenges is that there may be some missing classes. Like there's going to be samples that were never ranked as a 3 or a 7. So what do you do then? Does that make sense? Okay, so think about that. Maybe it's something difficult, or maybe it's something easy. to solve. All right, so let me create the link. All right, so I'll put it here under KNN. New assignment. So I'll just call it KNN homework. Right. All right, so today's the 28th, Wednesday. So this will be due 4th, 10. Stay open. Sunday. Okay. So using the provided line quality data set, train and test a KNN model. So we provide line quality data set. Provide performance metrics. And precision with F measure and the submit a report with all right. Is this clear enough, guys, as far as the homework description? So using the provided wine quality dataset, train and test a KNN model as described in class. Provide performance metrics such as precision, recall, F measure, and the confusion matrix. Submit a report with screenshots and comments of your work. All right, and I need to attach the file. So I'm going to do okay, wine quality. All right, so I added the file here, wine quality. Wine quality, right? All right, and that should be it, right? So, yeah, so today we covered KNN, as I said. It's your first machine learning algorithm. It's definitely one of the easiest ones, right? So there will be a few others that are a little bit more complicated. but definitely powerful still. A good algorithm. All right, so we've completed our first algorithm and we're going to move on now. Next week, I'll introduce unsupervised learning and k-means. So that'll be the topic for the Monday lecture. And now you have your second homework assignment, which is KNN using the wine quality data set. All right? All right, so I'll end this recording here.